Hello, welcome to our LinkedIn live session. Hope you are all doing great today. My name is Neil Kanungo. I'm your host. I'm joined today by Daniel Baker, our head of evangelism. Daniel, do you want to say hi?
Hey everyone, looking forward to the session.
Hey, well, it's good to have you, Daniel. Today we're going to be doing a great session. We're going to be doing image similarity search in vector databases, and I really like this exercise because it is a great visual way to really confirm that the similarity searches and results that you're getting are very accurate and relevant to your queries. So we're going to be looking at MRI scans, and we're going to be pulling up different scans that are similar to a query scan and be able to detect healthy brains that might have tumors or different diagnoses. Again, a great visual example. So if any of you would like to follow along, there is a KDB AI Cloud Starter Edition. And so as we get started, you can go ahead and sign up for KDBI Cloud Starter Edition by going to kdb.ai in your browser. And at the top right, you'll see the sign up. And there, you'll be given a sign up form. Fill out that form. You'll be sent an email that you click on. And with that email, then you'll receive one more email that will show you how to log in with cloud.kdb.ai. And when you get there, you will see your API endpoint and you will see your API key. Make sure to keep that key somewhere safe so that you can always access it. You're only able to copy it when you create the key. So it's good to kind of put that in a notebook somewhere. And that will give you what you need. You know, if you have your Python environment set up already, we're assuming that you do. If you don't, you can go into our documentation and go into the prerequisite section and learn how to set up your Python environment. But everything we're doing today is going to be in Python, and you'll be able to access via API your kdb.ai vector database. Now, one quick thing I did want to mention is that the LinkedIn streaming can be a little funky sometimes, and it can kind of restart or kind of show different time points. It can lag. And so if you're having any issues with our live stream, just hit the refresh button on the LinkedIn Live page, and that should bring you to right where we are. So if you have any issues, if you're continuing to have issues, you can also jump to YouTube. We are simultaneously streaming to YouTube, and you can catch this live stream there as well. It's actually a little bit higher quality, so I recommend watching on that as well. And the recording will be on YouTube after the session as well. So with that, I wanted to talk about our session today. We are going to do a sample on the Learning Hub. Apologies, this arrow is pointing to recommendation systems. We're actually going to be doing the image search one, so ignore this arrow here. But go to kdb.ai and you go to the image search sample. And then in the image search sample, there is a button to download from GitHub. That'll take you to a notebook, a Python notebook that you can download, and you can follow along with us. It's encouraged that you get hands-on with this. That's the best way to learn, in my opinion. But you're welcome to just kind of watch along and passively just kind of view and learn about the image similarity search that we're going to be doing today in kdb.ai. Now, before I jump in, I've shortened my introduction a bit because I've gone over a vector database intro the past couple sessions. But today I wanted to just quickly touch on a couple key concepts. The first concept is that your vector database and your embeddings, your data is coming in. You're passed through an embedding model, which creates vector embeddings that are stored in your vector database. So that happens outside your vector database, the embedding process. And then the query happens by your application. The query will also go through the embedding model, go to the vector database, and then you are able to post-process results if you'd like and surface those to your application. Now, vectors are, in their simplest form, they have magnitude and direction. So shown in 2 dimensions, it's shown here with vector going to 1, 1. In 3 dimensions, it's going to 1, 1, 1. These are 2 and 3-dimensional vectors. We can't visualize 4-dimensional vectors, but these vectors that we're using, these embeddings that we're using, and when I say embeddings, those are kind of synonymous with vectors. These embeddings that we're using have many different numbers in them. They can be thousands of dimensions long. So not something we can visualize very easily, but it gives you an idea of how the vector database works. It's actually using similarity scores and similarity metrics to find vectors that are related to each other in your vector database. And that's really powerful because traditional databases work with exact searches, exact matches. But when you're able to find similar matches based off of semantic meaning, you're able to surface data that's like other data and surface a lot more meaningful data and a lot more data that can pertain to your application. So it's very powerful, and we're going to see that today. So your data will go through an embedding model. There might be different models that you're using for audio, video, text, images. You can even use like flat files and structured data as well. These will create different embeddings, and you can picture these embeddings as being just these dots in your vector space. When you query this vector space, you're going to get a query vector that is maybe something like text, like a human readable text that goes through embedding model, generates that set of numbers, that high dimensional embedding, and then lands that query vector in your vector space to find the similar vectors. So this is showing finding the 3 nearest vectors to the 3 nearest embeddings to the query vector. So with that quick introduction, I wanted to go ahead and hand off to Dan Baker, and Dan is going to be showing you today how to do image similarity search. And Dan, I'm going to bring your screen on, and if you could actually before we get started, if you could zoom in a little bit to maybe 150%, I think that might make it a little bit easier to read.
Is that okay?
Sometimes live streams, yeah, that looks good. Maybe one more notch actually, is I think sometimes, yeah. Is that going to work for you, or is that too close?
It's fine. It's fine. We can work with it.
Okay, great. Yeah, I think sometimes the live streams are a little bit lower resolution, so this should work well. So with that, Dan, I will hand over to you, and let's dive into our brain MRI scans.
Awesome. Thanks, Neil. And I've got to say, that was a brilliant introduction. I'm not sure I've got much more I can add to that, but I'm going to try. So, hey, everyone. My name's Dan, and I'm the head of evangelism at KX. And today I'm going to be walking through a demo of image similarity with KDB.ai. Now, just to reiterate, for those that want to follow along, hopefully you've just followed Neil's steps and now have an instance of KDB.ai up and running. Now, you're going to need your API key and your endpoint because we're going to need this later in the demo. You're also going to need to pull down the notebook from GitHub and run through the prerequisites listed in the repo README. Now, I've done this ahead of the session. So what I'm going to do is I'm going to go back into my notebook and import the packages that we're going to need for the demo. So to do so, we're just going to select the first code cell and then hold Shift and Enter to execute through them. Now, you may end up getting a TensorFlow warning. Don't worry about this. This is predominantly complaining about GPU drivers and will not affect the demo today in the slightest. Okay, so I'm going to navigate through. We've also defined a couple of helper functions, and this is going to be used to visualize our images in the demo. Now, as Neil said, we're using Python, and I'm going to assume a basic level of Python understanding. So what I won't do today is go through each code cell line by line. Instead, what I'm going to do is conceptualize the ideas and the rationale behind what we're doing. So with that, the data set that we're going to be using today contains a series of brain scans that have been pulled down from Kaggle. The rationale being that when we apply it to a powerful vector database such as KDB.ai, medical professionals will be able to compare scans against others and hopefully help diagnose tumors. Now, to save time, we've taken the liberty of resizing the images so that they're optimized for model training. We've also defined the pixel intensity and renamed the images to correspond to the tumor type. So with that, let's go back into the notebook. And what we're going to do is we're going to extract our image file paths and then use the plot image function to visualize the results. So again, back into our notebook, we're going to run through the cells. Let me just finish off this cell here, and let's explore what we've got. Now, I'm just going to, sorry, Neil, I'm just going to make this slightly smaller so I can see it on my screen.
There you go.
What we end up with is 4 categories. We've got meningioma, which, as you can see, is quite obvious in this large tumor here. We've then got no tumor, which is a nice, clean, healthy brain scan. We've got glioma, which you can see this mass here, and it actually looks like there's another little mass to this side of the brain too. And then you've got pituitary. Now, bear with me here. I'm just going to talk about this a little bit because it'll make sense later in the demo. Now, the tumor is not this dark matter here. This is actually part of the hippocampus, and it divides the hemispheres of the brain. The pituitary gland is actually at the back of the nasal opening. So it's this dark matter here. Now, again, it makes sense why I've gone into detail a little bit later in this demo. But ultimately, what we've done is we've saved each of these images with a new class label from one of the above categories. So you can see we've got 394 files that belong to one of the 4 classes. Great. So let's now look at creating our embeddings. But before we do, let me just emphasize on some of the things that Neil spoke about previously with a 30-second elevator pitch. And this is just to make sure that we're grounded in vectors and their meaning, context, and function. So let's jump back into PowerPoint. So as Neil mentioned, a vector is just a mathematical way to represent a fixed length array of numbers that represent both magnitude and direction. Now, this can run into thousands, which is obviously cumbersome for humans to conceptualize, but perfect for machine learning applications. Vector embeddings, therefore, simply refer to a vector that contains a numerical representation of typically non-numerical data objects. So think things like text and images, video, or in this instance today, we've got our MRI scans. Now, these embeddings are used to capture the inherent properties and the relationship of the original data in a highly condensed format. For example, we know that images contain millions of pixels. Each will have a unique color, hue, and contrast. So our embeddings can therefore be used to encode the relevant information about the data into a lower dimensional space. And I guess the reason we do this is it ensures efficient storage, retrieval, and computation. Now, to create our embeddings, we need to transform our data through an embedding model. And again, as Neil said earlier in the session, there is a whole bunch of ways that you can do this, and it depends on the type of data that you're trying to convert. Because we're looking at images or MRI scans, which is effectively an image, we're going to be using ResNet 50. Now, ResNet is a type of ANN, or artificial neural network, and it's designed to recognize and classify images into object categories. It does so by analyzing the features of an image and then using them to make predictions about what the image contains. Now, it achieves this using a technique called residual learning. And it's a process of skipping over some of the layers in the network to learn the differences between their input and output. Anyway, let me try and break this down into how we've used it in today's demo. So to begin with, we're going to push our formatted images into ResNet 50. Now, again, remember, this isn't a single layer. It's many layers that are performing that residual learning. Then we have our flatten layer. Now, its role is to turn each image into a vector, and this is what we'll be storing into the KDB.ai database. Then finally, we have our dense layers. Now, these help create the 4-dimensional classifications of the input image. So if we look at the slide, we've got 1000, which is glioma. 0100 might be meningioma. 0010 might be pituitary, and so on. So let's jump back into our notebook. And what we're going to do is we're going to load the model from Hugging Face and then summarize the results. Now, while that loads, just for context, Hugging Face is a popular data science community that allows developers to easily incorporate machine learning models into their workflows and pipelines. So again, if you get an error, don't worry about the JSON. It's going to work fine. So let me go ahead and run the model summary. Now notice the 4 layers that we previously discussed. We've got our functional layer, the flattened layer, and the 2 dense layers that perform image classification. In all fairness, we don't actually need the classifications in this demo. So what we can actually do is strip them back using the pop command. And if we run this, you'll see you're left with 2 results, the functional layer and the flattened layer.
Could you zoom in just a notch there, Dan?
Yeah,
If you don't
sure.
mind?
So we can see that we've gone from the 4 layers, the functional, the flattened, and the 2 dense. This converts it into the 4 category types. We then remove that using the pop command, which leaves us with our original ResNet functional layer and then the flattened layer. Everyone still with me? Awesome.
Yep.
So let's now create our embeddings by iterating through our data set and saving them to a corresponding class vector. So again, I'm just going to start on the top cell and I'm going to run through each of these cells here. Now, bear with me, this is going to take a little bit of time. What's happening here is all the images are being pulled in. So ultimately what's going to happen is it's going to get our embeddings, it's going to retrieve the class label, it's going to set the tumor types, it's going to store the files into alphanumeric order, and then finally what it's going to do is it's going to output the files via a data frame. So what we would hopefully, or what we would expect to see at the end of this is 394 files that sit within 3 columns. You'll have one for the source, one for the class, and then one for the embedding. So we're nearly there. We'll just give that a few more moments. And that is just finishing now. Always takes longer when you're live, right? So we're just getting there. So 394, we can see that's now being created. And as we suspected, we've got our 394 records broken into 3 columns, one for our source, one for our class, and one for our embedding. So now what we're going to do is we're going to visualize this. To do so, what we're going to do is, and this is just for our benefit, we're going to reduce these embeddings down into 2 dimensions. And then we're going to plot them into a simple cluster chart. So I'm going to go ahead and run the cells. And we'll just wait for that to finish. So we just give it a second. It's going to shrink that down, okay, into 2 dimensions, and it's going to plot this out. Now, sorry, Neil, I'm just going to shrink my screen one more
no
time.
problem. Yeah, we'll zoom in. Yeah.
But this is where things get interesting. Okay, so notice that glioma, we'll get everything on the screen there. Notice that glioma, meningioma, and no tumor, they're fairly well clustered. But pituitary seems to be dispersed. Okay, this goes back to what I was talking about earlier in the session. Now, it's likely that this just means that more training is required, but it could also mean that a misdiagnosis has occurred. You know, the point I'm trying to make is that even with minimal training, the AI model has uncovered something that may have been missed by a medical professional. So, you know, it's a brilliant tool for, you know, situations and verticals in the industry like this. Anyway, let's move on and get our embedding stored in the KDB.ai. Now, to do so, you're going to need your endpoint and API key. Now, I've already added these as variables, but if you are following along, go ahead and paste them into your notebook now. Okay, so we can see that they've gone in. So the next thing that we want to do is define the vector DB table schema. So I'm going to run the cell, but pay attention to 2 things. We want to pay attention to L2, our method of similarity, and HNSW, which is our index type. In fact, what we'll do is let's jump back into PowerPoint and quickly discuss these. So in this instance, we're going to be using L2, which is Euclidean distance. Now, this effectively assesses the similarity of 2 vectors by measuring the straight line distance between the 2 vector points. Simply speaking, the shorter the distance, the more similar the vector. For our indexing, we're going to be using HNSW, or Hierarchical Navigable Small World. Now, think of this as a type of proximity graph that connects vectors into a network-like structure. So you've got each vector connects to its peers and builds a friends list. So when a query comes in, it traverses the graph until it finds its nearest neighbor to that inbound query. Now, again, please don't worry if this is new to you. We've got plenty of documentation about these methods over on the KDB.ai Learning Hub. We've also got our Slack channel should you have any further questions. Anyway, let's jump back into the notebook and add our embeddings. So we're going to come down and we're going to create our vector table. So that's gone in. We are going to create the table. Now, this again will take a moment. While we wait, let's just talk about the next cell. Now, as a side note, when you're adding larger amounts of data to your index, you're typically going to want to break these up into chunks. In fact, I think you spoke about this last week and the week before, didn't you, with Michaela and Nathan? But effectively, what that's helping you do is streamline vector processing and subsequently reduce computer load. Now, 10 megabits is the recommended size. We can see that we're coming in at just over 6. So no chunking's needed. We're good to just go off and get that embedded into our table. So let's wait for that to update. We can see that's gone in. And now I guess what we want to do is just verify that our data insertion has taken place, which again should hopefully yield our 394 embeddings across the 3 columns. All good?
Looks great.
Awesome. Awesome. Okay. So now what we're going to do is we've got our embedding stored into KDB.ai. Let's test them out by filtering for images that contain the word glioma. So again, we're going to run this query. And we can see that this returns a table of 100 embeddings. Now, in all fairness, this is searching via the file name, which isn't really what we want to achieve. So we're going to run this again, but this time using a similarity search. Okay, so what I'm going to do here is we can see I'm looking for image 40. I'm going to stick with image 40, but if you're following along, feel free to change this to any sort of number you want. Either way, what will happen is the vector data will be saved into a new variable in which KDB.ai will perform a similarity search. So again, it's pulled this data in image 40. It's doing it sort of sequentially. So it's come up as 45 is a glioma tumor. It's then pushed that into KDB.ai by creating an embedding, and it's performed that similarity search. Now, the result is the 8 nearest neighbors that are formatted into a table, which again, in this instance, has all come back as glioma. Of course,
and you can actually see those nearest neighbor distances.
Yeah.
In the table,
you can see the nearest neighbor distances in the far column. And the nice thing is we can also plot these images, so we can get a nice visual representation too. And this is where it's really going to help medical professionals. So they've created the original image that's being scanned in, an embedding's being created, and then again it's pulled up the nearest neighbors for someone to be able to go in and compare. Now, again, it's interesting because if you look at it, some of these are looking down from the top down, some of these are looking from the I'm assuming that's the back of the head. Some of them come back looking at the front of the head. So, how ResNet has picked up what classes are which and then how the embeddings have worked, there's a little bit of magic involved there. But again, it just goes to re-emphasize what I said before. It highlights the amazing capability of AI and the potential in fields such as medical image recognition. Okay,
and before we hop to the next part of the demonstration, Lewis had a question here. He says the image you're querying in here in the training set, and I think that is an interesting question because we're not actually training a model here. We are basically, you could say, like encoding the data. We're embedding the data from the source data into a vector format, an embedding format that we can do similarity searches on. So we're not training a model and applying that model to new data. If we wanted to, we could bring in all sorts of new visualization or new images as well. And that would look very much like the same process here. But all you're doing is taking those images and you're putting them through the embedding model, and then you're finding similar images from that. So the embedding model does that the actual encoding, and you're not, again, I won't, I guess, repeat it too many more times. You're not actually training a machine learning model in this instance.
Yeah. So what I'll add to that, Neil, is we trained the model previous to this session, and we actually have a notebook with all of the training data in there, which we will polish up and then we will publish. In terms of what images we're using in the notebook, what comes accompanied with the GitHub repo is the training data set and the testing data set. And in standard sort of data science, you would do like a 70-30 type split. So that's all been done, and we'll look to publish the testing notebook once that's gone through a little bit of QA and cleaned up. Anyway, conscious of time, so let's quickly try one other example. So this time I'm going to select image 210. Now again, in this instance, what's come back is meningioma. So again, we've pulled out an image 210, the embedding's been created, it's then gone through the nearest neighbor search. Meningioma is what's come back. And again, you've got side of the skull, you've got top of the skull, you've got back of the skull, but on each of these you can see a quite significant tumor type in there. So hopefully that gives you an indication of the power of what this technology can do. Now, as we wrap up, firstly, I hope that you found it informative and now ready to dive into the world of vectors. And I just want to remind you, if you do want to learn more, don't forget that we have some awesome resources over on the KDB.ai Learning Hub. You can also subscribe to our YouTube channel and follow the K Experts here on LinkedIn. Or why not meet us in person by coming along to one of our upcoming Vectorize events. They're running throughout 2023 and 24 and taking place all over the world. In fact, our next will be in London next Thursday, where we have some amazing presenters lined up. And honestly, I'd love to see you there. Finally, I just want to have a quick shout out to the awesome team of people who've been instrumental in building out these samples. This includes our pre-sales team, engineering, R&D, and of course, evangelism. I think they've all done a fantastic job, and I'm confident that their efforts will reduce your own learning curve. Anyway, thanks again for your time today, and I look forward to connecting with you in the future. So, Neil, back to you.
Thanks, Dan, for that great sample. I think, again, that shows the similarity search in action. You're able to see the tumors come up that are the same type of tumor, but only by querying by image, not by querying by keywords or tags. So it's very powerful in that way. You're able to detect things or assist physicians with the detection of new things, new diagnoses. Now, this can be used in a variety of industries. It can be used in wafer manufacturing, semiconductor manufacturing. It can be used in detecting defects in other manufacturing processes. There's a wide array of different image recognition and image similarity use cases out there. So feel free to adapt this notebook to your own needs. We are going to be doing another session next week, the same time, Wednesday at 11:30 Eastern. It's 8:30 Pacific and 4:30 p.m. UK time. And speaking of UK, make sure that if you are in the UK, and you're in the London region, come to that meetup that Dan mentioned. It's going to be a lot of fun. There's going to be a lot of developers there. It's a great way to learn. We'll do a hands-on vector database workshop and have some great speakers there as well for fireside chats and networking. So next week, we will do a pattern similarity with vector databases workshop online, and we'll do that through a LinkedIn Live session at those times I mentioned, 8:30 a.m. Pacific, 4:30 p.m. UK time. So we hope to see you registered for that. I'll be sending out the registration and setting up the event for this later today, and you can sign up for this. And then just a quick overview of what we have coming down the pipe. We have pattern similarity on October 18th. On October 25th, we're going to be doing LangChain and retrieval augmented generation. So that's how you can actually chat with your data through natural conversations. It's probably one of the hottest use cases of vector databases. And so we're really excited to present on that. And then on November 1st, we have sentiment analysis. And as more sessions are prepared, we will announce those in our upcoming sessions. So just stay tuned. Thank you all for joining today. We really appreciate your time, and be sure to try out that sample and sign up for KDB AI to get your vector database started. And thank you, Dan, for your time today.
No problem.
And great demonstration. Thank you.
Thanks, Hill.
Bye.